Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Wedding Ring, LSA Reflections. As always, please be an attentive listener while watching this video. So this problem deals with a custom-made wedding band as shown below, and the shape is obtained. First of all, you're going to revolve a rectangular, there's no first, I guess, but you're going to be revolving this rectangular region around this axis, and you're also revolving this curved piece here, which you're going to see is a circle. So you're revolving that around a vertical axis. So the inner radius is called R, as here. It has a minimum thickness, which is this dimension of the rectangle, and the width of W, and W is this up and down distance here. The curved boundary, which is this part here, is the arc of a circle whose center lies on the axis of revolution. So the center is there. And these are some values that you can have for these, and these are considered typical values. People that have very big hands or a lot of money to spend might do something very different than this, but these are some values that you see R, T, and W ranging around. Anyway, the first problem first part of this LSA says, use calculus to determine what is the volume, and this is V as a function of R, T, and W. And notice that the units here are in millimeters. That becomes important. Now, without loss of generality, engineers usually impose a coordinate system. Here's a good coordinate system to use. So we're assuming this is centered at 0, 0. That means the circular arc is centered there. And we've got, we go from minus W over 2 to plus W over 2. And we're going around the y-axis, and so this is our superimposed coordinate system. And if you think about that, the radius of this circle, you go from here to a point on the circle, so you go out r plus t, so that point is called r plus t, and the height is half of w, so that is w over 2. Similarly, down here, you would have this point would be r plus t, and this would be minus w over 2. So that's sort of what we're dealing with here with this picture. And please note that what you have here is a right triangle. You go here, up here, and there's the hypotenuse. So you see that's going to be able to help you determine exactly what is the radius of this circular arc. And here's that picture. So this dimension was r plus t. This is w over 2. So the radius is the square root of r plus t whole squared plus w over 2 whole squared. And so that's what you're going around. And the way I approach the problem anyway, I do these two things separately and then add them together. So I'm doing the circular piece first. So that's this is little circular, actually this is called a circular segment because we have a chord there, and then we have this boundary, this is circle. So we have the line and then the circle. So that's what we're going to do, and we're going to use the disk method. So there we're going to strike the slice perpendicular to the axis of revolution. That means we're doing dy. Okay, and the formula was pi r squared. So the outer radius, you go from here all the way to the circular part, but we figured out that that radius was this. So it is pi r squared, and when you square that, you just get rid of the square root, and you're going to be integrating from minus w over 2 to w over 2. And then you're going to be subtracting off the inner radius. Now the inner radius here is, we're really just calculating this little segment, circular segment. So the inner radius is going to be r plus t whole squared, and it's pi times that dy. Now what we're doing is, first of all, please observe that this thing cancels out exactly with that thing. So you just have w over 2 whole squared, but w over 2 whole squared doesn't have a y in it. And so what you're really doing is you're integrating a constant, w squared over 4, over an interval, and tradecraft from Calc 1 is if you integrate a constant over an interval, it's going to be the constant times the length of the interval. Well, the length of the interval here is w, and so this integral is just going to be pi w cubed over 4. And so that's what we're getting for this, pi w cubed over 4. Now, we just dealt with a circular segment, and so now we're going to deal with this rectangle here. Well, the outer radius is r plus t, and the inner radius is just r, and so pi r squared again. We're doing the disk method, and so we do the rotation as pi. Here's the outer radius squared, here's the inner radius squared, and again, notice that when we expand this, we'll get r squared plus 2rt plus t squared. So that's what there, and then we're subtracting off r squared, so there's some nice cancellation that goes on. So we have 2rt plus t squared is this constant, and there is no y there, and so we're integrating that from minus w over 2 to w over 2, so that's just multiplying w times all of that, and there's the pi. And if I factor out the w, I'd have pi, this business, and then w. And that's the end of this part 1. So the total volume in cubic millimeters is V of RTW is pi over 4 W cubed plus pi 2RT plus T squared times W. The problem goes on though. So suppose the jeweler plans to charge the customer a 250% markup on the material cost of and they're using an alloy, so it's 90% gold and 10% silver that they're going to use in the ring. Now, this is common for them to do a markup like that because there is labor involved, and they're just charging you mostly for, well, actually, they're charging a lot for the labor, but it's a 250% markup on the material cost. Now, this is common, and I tried to make a little bit of a joke that love not only hurts, but is expensive. The inner radius is determined by the measurement of the customer's finger, and the jeweler makes all wedding bands, this particular jeweler, with T equal 1 millimeter. And I did look up on the day I wrote this gold and silver prices on that day, and that's what we're using. So as of the writing of this, the US dollar values per, the units are different, per troy ounce are shown below. And so gold was $1,827 and change per troy ounce, and silver was $21.21 per troy ounce. Now, the prices do fluctuate a lot, but the science really doesn't change. The density of gold and silvers are 19.3 grams per cubic centimeter and 10.5 grams per cubic centimeter, respectively. Now, again, we have cubic centimeters here, and we have cubic millimeter somewhere else, so we do have to deal with that. So the broad question is, for a given and acceptable cost in US dollars, what is the maximum width, W, of a wedding band that someone could afford? Okay, and I ask you to proceed in the following way. Measure your left ring finger to determine R. And I do want you to do this in a way where you don't have to cut off the finger, and what you can do is you can take a string, wrap it around your finger, but then you have to say, oh, my finger is, that really is a circumference of something. It's more or less like a circle, so you do have to divide by 2 pi when you get this number. So that's a way to do this. And then I also ask you to choose a cost representing what you expect your significant other should be willing to pay. Now, that's a little bit of a game, and your answer will be different than other people's answer, but I will address how we approach that problem, and so everybody should be good with that. Then what we're supposed to do is use the fact that 1 pound is what is called 12 troy ounces. This is a different unit. This is not your 16 ounces per pound. This is 12 troy ounces, and that's what they have in the jewelry industry. 12 troy ounces corresponds to 453.59 grams, and a pound is that as well. So 1 pound is 12 troy ounces, and that's almost 454 grams. And we're letting T be 1 because that's what the jeweler does. And so we want to find the width to the nearest millimeter. Now realize that you see T was 1, you measured R, so the only variable that you have left on your equation from the previous slide is W. Okay, and then I ask you to use Newton's method from Calculus 1 and perhaps Excel to compute the width to the nearest millimeter using your cost, however you thought people could pay, and your R. And then I ask you to upload your spreadsheet as a PDF. And again, we talked about Newton's method in an earlier LSA discussion, and we're going to, and it's a Calc 1 topic at the College of DuPage. Okay, so here we first of all, it's an alloy, and so the density of the alloy is going to be different. And so it's going to be 90% gold, and it's going to be 10% silver, so you do a weighted average of those two. And so the alloy is going to come in at 18.42 grams per cubic centimeter. But a cubic centimeter is something that, you know, a cubic centimeter would have a centimeter, a centimeter, a centimeter on all dimensions. And you know that a centimeter is 10 millimeters. So this 1 cubic centimeter is 1,000 cubic millimeters. Okay, so up here we found out when we did the weighted average that the density of the alloy was going to be 18.42 grams per cubic centimeter. But when we change that to cubic millimeters, we're going to be dividing by 1,000, so we move the decimal point 3 places left. Okay, so that is good. And then what also happens is the cost is also a weighted average of the material. So 90% of it is gold, but 10% of it is silver, so you do a weighted average, and you get that the material cost per troy ounce is 1,647 and change US dollars. But you see, when we have grams up here, so what you really want to do is say, well, how many troy ounces are there per gram? And you can look this up, or you can do division with the numbers that I have for you. But we have, this is the cost per troy ounce, but there are 0.032151 troy ounces per gram. So you see the material cost per gram is the product of these two. So you take this number times this number, and this is the material cost of the alloy per gram. Now, the jeweler does do a 2.5% mark, not percent, a 250% markup, 2.5 times. So you take 2.5 times that number, and that means the price to you per gram is 132.38, and all of those numbers. So that is the price to you per gram. Okay, now at this point in time, just to move ahead, I decided to take the ranges. So this is the small value of R, and this is the big value of R, and this is the small value of W and the big typical value of W, and you get that. And so for those volumes, I plugged that into the formula that we had on the previous page. And again, T was 1, so T is 1, R is 6, W is 4 here, and T is 1, R is 12, W is 10 here. I plug that in. This is your volume. Now this is your volume in cubic millimeters, so we have to take the number up here, grams per cubic millimeter, and multiply that times the volume. That gives me the number of grams in your ring, and then I take the number of grams in your ring times the price to you per gram, and so, you know, like 4 times this number is this number. And so we get kind of a range of things here. Now, that wasn't exactly what I asked you to do. What I asked you to do was measure your finger and go through a calculation like that. And so what I did is I said, well, pretend, and I have chubby fingers, so pretend your figure, and that is after you divide by 2 pi, but you end up with the 12, kind of a chubby finger. Okay, so you've got a chubby finger. You know that R is 12, and again, R is whatever you came up with, and T is 1. And so the W now is a variable, and what we wanted to say is how much are you willing to spend? Now, that really depends on you too, but here we can see there's kind of a range here, and I'm just, for sake of argument, going to say, suppose you were willing to spend $3,000. What would you do? Okay, so you have to take the grams per cubic millimeter times the cost per gram times the volume. And then you're going to subtract 3,000, and you do some simplification here, and you get equations, you get coefficients, and by the time you multiply all those things together, you'll get 1.91 and change w cubed plus this number times w minus 3,000. And again, when you're doing Newton's method, you are seeking a zero of the function, and so you have to subtract the 3,000 across to the other side. So now we're going to do Newton's method on this problem. These are the formulas that I used, and so I take my initial guess to be 8, and I go through, and over here I'm looking at the absolute value of the difference, and I'm using my recursion relationship that x in plus 1 is equal to x in minus the ratio of f of x in over f prime of x in, and there I calculate the ratio and things like that. Now these are just formulas. Here are the numbers. Now the function simplified to be this, and I am subtracting the 3,000, so I really am looking for a zero of this function, and the derivative of this function would be this function that you see down here. So those were the formulas that I put in and showed you on the other page. But as you normally see, that Newton's method converges really pretty fast. And you see that 8 wasn't a bad guess, and although it ends up being closer to 9. And in fact, if you're being really precise, you could spend 8.81, and you see that's when this really converges totally. Now, before there's a wedding band, there's often a diamond engagement ring. And so the diamond engagement ring usually have a gold alloy plus a diamond, and you know from your chemistry that this is carbon, and it's a whole different analysis. There are many more parameters here. There's the weight of the diamond, which is the weight usually, and they use units that are called carats. And there's the clarity of the diamond that influences its value. There's the cut of the diamond, and there's a color of the diamond, and wow, there's a whole bunch of stuff here. That's probably too much for Calculus 2, so we'll do that in Calculus 3. Actually, we probably won't do that in Calculus 3. But anyway, there is a lot of interesting math in cutting diamonds, though, and stuff, but that's not what we're talking about here. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself, because self-care is important. And take care of each other, because we're all in this together. God bless you all. Look forward to seeing you soon in class.